This is section 4.7, medians, altitudes, and perpendicular bisectors. So we begin this section with some definitions of what those three things are and examples of them. First, a median. A median of a triangle is a segment from a vertex to the midpoint of the opposite side. So you see in triangle ABC that I have drawn on the right here, the green line that I've drawn from point A to point M is a median because I know M is the midpoint of side BC. I know it's the midpoint of side BC because I've marked that BM is congruent to MZ. So here, segment AM is a median from vertex A to side BC. There's only one median from every vertex to the opposite side, because there's only one midpoint of the opposite side. So the median is the line segment that connects that vertex to the midpoint of the opposite side. An altitude of a triangle is the perpendicular segment from a vertex to the line that contains the opposite side. So the median may not be perpendicular to the opposite side. An altitude has to, by definition, be perpendicular to the opposite side. But that means it's not going to hit necessarily in the midpoint. In an acute triangle, if you have a triangle in which all three angles are acute angles, smaller than 90 degrees, all three altitudes are inside the triangle. So in this first triangle I've drawn here, I've drawn one altitude in red, because it goes from this vertex up here to the opposite side, and it makes a right angle, so it's an altitude. It's perpendicular to the opposite side. I can draw another altitude from a different vertex. So if I take this vertex and I draw the altitude to the opposite side, I'm going to draw it so that it's perpendicular to the opposite side. That's another altitude of the triangle. It's also inside the triangle. I can draw a third altitude because I have a third vertex, and I can make its altitude to the opposite side, where it is then perpendicular to the opposite side. So in an acute triangle, there are three altitudes, and all three altitudes are inside the triangle. In a right triangle, two of the altitudes are actually sides of the triangle. The altitude from point E up here to side FG at the bottom is side EF, is the only perpendicular segment from E to the line that contains FG. So EF and side FG are both altitudes of the triangle. FG is the altitude from point G side EF. It's segment from G that's perpendicular to the line that contains EF. So in a right triangle, two of the altitudes are actually sides of the triangle. The third altitude is inside the triangle. If I take the altitude from F to EG, I get a segment inside the triangle. It's perpendicular to EG. So in an acute triangle, all three altitudes are inside the triangle. In a right triangle, two of the altitudes are sides of the triangle, and the third altitude is inside the triangle. In an obtuse triangle, everything goes haywire. And two of the altitudes are actually outside of the triangle. And that's why in the definition we say that the altitude goes from the vertex to the line that contains the opposite side, because it may not actually touch the opposite side. So here's an example. If I take the altitude from point L, vertex L up here, to the line that contains NK, well, it has to be perpendicular, so it has to go, in this case, straight down, KN. That does not touch the side of the triangle, it is KN. Instead, if I extend AN and look at the line that contains it, then that altitude is perpendicular to that line. So that's the only way I'm able to get a right angle there, is if I extend the side. But the altitude is actually outside the triangle, because I have an obtuse angle at angle K. I have another altitude outside the triangle if I take the altitude from point N. If it's going to make a right angle with the side that contains LK, then it's going to be outside of the triangle like this. So in an obtuse triangle, two of the altitudes are outside the triangle. The third altitude the one from point K is inside the triangle, and it's pretty boring like that. So every triangle has three altitudes. Depending on the size of the angles, the altitudes may be inside the triangle, outside the triangle, or the actual sides of the triangle itself. And our last definition for now, a perpendicular bisector. A perpendicular bisector of a segment is a line, or it could be a ray or a segment, that is perpendicular to the segment at its midpoint. So there's two pieces. It has to be perpendicular, and it has to hit it at its midpoint so that it's also a bisector, cutting it in half. So I've drawn a segment here. I've drawn segment PR. And I've labeled its midpoint. Its midpoint is M. I know it's the midpoint because I've indicated by these hash marks that PM is congruent to MR. So I have the midpoint. The perpendicular bisector then is going to be a line or a ray or a segment that's perpendicular to PR at the point M, because that is the midpoint. So I can draw that like that. Draw a line or segment that is perpendicular to PR at M. How many of them can I draw? In certain plane, I can only draw one. I can move a different plane and draw a completely different one. But in certain plane, I can only draw one perpendicular bisector. Okay, so the perpendicular bisector is perpendicular to the segment at its midpoint. Make a right angle at the midpoint. Alright, now 4 theorems about these things you just find. First theorem. If a point lies in the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. This makes much more sense by looking at the picture. So I have segment BC that's horizontal there in blue. I've labeled its midpoint as M. I've drawn the perpendicular bisector, which is a line PM. Perpendicular at M, and M is the midpoint, so it's a bisector. What this theorem says is that if a point lies on the perpendicular bisector, so I'm going to take point P as that point, then P, that point, is equidistant from the endpoints of the segment. Equidistant means it's the same distance. So that means the distance from P to B has to be the same as the distance from P to C. So those two need to be the same, according to the theorem. The reason this theorem follows this chapter on congruent triangles is, as you might tell by the picture, because we prove it using congruent triangles. We form congruent triangles like that. And we can prove that P is the same distance from B as it is from C. Our next theorem is the converse of that previous one. It says if a point is equidistant from the endpoints of a segment, so if I have a segment and a point, that point's just as far from one endpoint as it is from the other, then the point lies on the perpendicular bisector of the segment. If I have segment EF drawn there in blue, we've got a point P, and I've indicated that P is the same distance from E as it is from F. Then, so I've satisfied the hypothesis, according to this theorem, P must lie on the perpendicular bisector of the segment. So if I were to draw a line through P down to EF, then it must hit it at a right angle. It must be perpendicular, and it must hit it in the midpoint. So that point must be the midpoint, according to this theorem. P has to be on the perpendicular bisector. Alright, one little minor definition. The distance from point to line is the length of the perpendicular segment connecting them. If I have a line and I have a point, the distance from that point to that line is the length of the perpendicular segment that connects them. If I want to know the distance from P to segment MO, I'm not going to measure the distance from P to M, and I'm not going to measure the distance from P to O, because if I were at P and I was moving towards that segment, I'm going to go the shortest distance I can, and it's going to be go straight down, MO. And straight down is a perpendicular line. There we go. So that's how I would measure the distance, is to go straight from P perpendicular to MO. That's going to be the shortest possible way to get from P to MO. That's what I mean by the distance from a point to a line. Okay? So the next theorem, if a point lies on the bisector of an angle, when the point is equidistant from the sides of the angle. Analogous to the previous theorem that dealt with a segment and the bisector of a segment. This time, we're talking about an angle, and we're bisecting the angle. If a point lies on the bisector of the angle, then the point is equidistant from the sides of the angle. So I have my angle ABC drawn in orange. I've drawn in black the bisector of the angle. I know it's a bisector because I've indicated by these marks here that it's dividing the angle into two congruent angles. According to this theorem, P has to be equidistant from side BA as it is from side BC. So if I were to measure the distance from P to BA, which I just learned I do by drawing the perpendicular segment, then that distance needs to be the same as the distance from P to BC, which again I get by drawing a perpendicular line. So that needs to be the same as that according to this theorem. Turns out the converse of this theorem is also true. So that's our last theorem. If a point is equidistant from sides of an angle, then the point lies in the bisector of the angle. So now my angle ABC is in blue. P is some point in between that's equidistant from BA as it is from BC. So the distance from B to X is the same as the distance from B to Y. If that's true, then the conclusion of this is true. And the conclusion of this is that P must be on the bisector of the angle. So if I draw the bisector of my angle, P must be on that. That angle has to equal that angle, because P is on the bisector. These are four theorems that won't necessarily be used as often as some of our other theorems, but they're interesting because they follow from our congruent triangle. And so what we're going to do in class is divide up in groups and prove each of these theorems. So right now, what you need to do is use them and your definitions to complete the immediate practice problems. Fill in the blank with one of the following words. So they're always, sometimes, or never. And I've written at the bottom that you need to write down each statement in your notes. Number one, an altitude is blank, perpendicular to the opposite side. Fill in the blank with either always, sometimes, or never. Number two, a median is blank, perpendicular to the opposite side. Number three, in an acute triangle, an altitude is blank, outside triangle. Fill them in with either always, sometimes, or never. That is the end of section 4.7.